All right. So today we are going to be talking about a way to hack C programs, and basically this strategy that we're going to be using is called buffer overflow. But before we get into actually hacking the C programs, we got to first learn how C programs are run, so it'll be very fun. So just as a refresher, remember we go from this kind of code to assembly code to machine code, right? And essentially we want to find out and basically all of these instructions are stored somewhere, and then they store all their variables somewhere, and like they're at very specific places in memory. But how are they stored in memory? How are variables stored in memory? This is how it looks. Does anybody know what the stack is, or what's a cool phrase from CS that you guys know that has to do with stacks? Anybody? Come on, it's the name of a very good website. Nobody knows what the website people use for CS problems is called? Anybody? Oh, somebody put in the chat, maybe. Indeed, Stack Overflow. And does anybody know how you could get Stack Overflow when you're running your like Python program or like C++ program or something? Anybody know how to get a Stack Overflow? Or in Java? Does anybody no no one's ever gotten a Stack Overflow in Java or C++? Really? No, okay, well basically a Stack Overflow just means that you like call a recursive function too many times, right? You basically have an infinite recursion, and that's what causes Stack Overflow. And the reason why it's called Stack Overflow is because your computer has something called a stack, right? And that's basically where it stores all the variables for your function calls, right? So every time you call a function, it adds something to the stack. And then if you keep calling the same function over and over again recursively, the stack is just going to keep going, keep going, keep going, and it's going to hit the heap and the rest of the memory of your computer, and that's bad, right? That's what causes stack overflow. So essentially, in C programs, basically, it puts all your local variables and stuff in the stack to store it, right? So essentially, this is how it looks, right? You basically have this is how your stack looks. If you want to call a function, you put your arguments in the stack, you put some stuff in, you put your local variables in the stack, and and then you put your code at the very bottom. So why is this relevant? Okay. Well, essentially, we could do something very clever. So my slides are kind of out of order, but let's just say we have the C program, right? And essentially, we have a local variable I and a array of characters buff, right? And essentially, we get to read in the character buff. Okay. So essentially, let me show you a cool diagram so that might help you guys figure this out. Okay, so essentially, if we could like have this, right, and we could override upwards, right? If we have our array here and we could override upward, which variable could we like change without which variable could we change just by inputting something here? So remember, we stack the local variables on top of each other, right? So I is on top of the buff. So what could we overflow? What could we change? Any ideas? No ideas? Well, basically the idea is that if we make buff long enough, we could like keep writing into this like character, this array, and then it'll go into the integer, right? It'll go into your next variable. So we could actually show this real quick over here. So right here, it reads in a string, an 8-letter string, and then it prints it out, and then it prints out the variable I, right? And I should never change, right? So if we like run this, and then we say AAA, whoops, not here, AAA, well, it prints out the thing we put in, and it prints out I, which didn't change, right? If we put in an 8-character string, still fine, right? But what happens? What do you guys think will happen if we put in a 9-character string of A's? Any ideas? No ideas at all. So just as a refresher, right? If we go back to the slideshow, your local variables are stacked on top of each other, right? So your I is here, your array is here, and we could keep if we keep adding A's, it's like A, and then it goes into here, right? So what do you guys think the value of I will be if we put an extra A, right? So it'll fill up the buffer, and then it'll go into the A. I mean into the int. It doesn't turn to 1, but it turns to a different number. But does anybody know what number it might turn into? So essentially in CS, right? Like every hey Chris, you know your ASCII, very nice. But yeah, basically every single character is encoded by a certain number, right? So A is encoded by 97. So essentially, it'll keep writing 97, 97, 97, 97, but once we get to the end of our array, it'll start bleeding into the integer, and it'll change the last byte of our integer into a 97. Does anybody know how many bytes an integer is? Just as a fun fact, how many bits is an integer? Come on, what's the biggest integer?
32.
Yeah, so integers are
Bits.
32-bit. Then how many bytes are there? If there's 8 bits in a byte, 4. Yeah. So
Okay.
essentially, okay. So let's just test that out, right? So, um, if we do nine A's, we get 97, right? Then what happens if we do 10 A's? Anyone have some epic hexadecimal skills? A. Okay. You can also tell me the expression for what it will be if we put if we put 10 A's, right? Now it'll override the last 2 bytes of our thing with 97. So what is that at the value? How do you convert? So how much is a byte like in base 2? What is it? If you have eight if you have 8 bits, how much does that correspond to at the power of 2? So essentially an integer is like 8 32 bits, right? So that's like if we put that in hexadecimal, how long is a byte? Yes, indeed. But if we have okay, if we're putting a 2 to the 32 thing in base 16, what is the length of it going to be? Any ideas? Well, let me give you a hint. Each byte can be represented by 2 hexadecimal characters, and A happens to be 61 in hexadecimal, right? So essentially, our integer starts off as eight zeros, right? Is that 8? 1, 2, 3, 4. 1, 2, 1, 2. Oh, extra. Okay. So essentially, as we override it, right, we're gonna override 61, then we're gonna override 61, and this is in hexadecimal, right? So what is this in decimal? Like, what do we predict it's gonna be? Come on, convert hexadecimal to decimal. Anybody? What math do I have to do? You can put the expression in the chat if you want. Convert base 16 to base 10. Anybody? Nobody? Okay, well, we could do the calculations out here, so it'll be like 16 times 6 to the 3, 3 plus 1 times 16 to the squared, plus 6 times 16 plus 1. So you should get 3809 if we put 10 A's. Let's see. Did I put an extra? I think I put an extra. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Oh, I did not put an extra. Oh, whoops, not that. 6 times 6 cubed plus 1. Oh, okay, I see. That makes a lot more sense. Yeah, okay, there we go. We just flip that around and we get our answer. Okay. So what happens if we put like, what do you guys think will be the difference if we put 12 A's and 13 A's in here? Any ideas? Well, basically the idea is integer is only 4 bytes, right? So if we override it with 4 A's, adding a 5th A is not going to do anything because it'll go past the integer itself. So if we do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and if we do that plus 1, it should not change. Okay, so essentially why is this relevant? Why is it relevant that we could change a variable that we're not supposed to change? Why do you think this is bad? Anybody have an idea why it might be bad to be able to change a variable you're not supposed to? Like what happens if I was like if it was reading in a password, right? Why might it be bad if like this is saying whether the password is good or not? What could we do to make our password seem good even if it's not? Anybody? like let's just say this is admin, right? And we're putting in our password. How could we change? We could basically make ourselves an admin just by overflowing the buffers, right? So that's basically one way you could hack C programs. Okay, so that's one thing. That's a good example of buffer overflow. But let's talk more about how code is run, right? So does anybody know what these two things are? And you know what? But you know what computer part these guys are? It is these are CPUs, yeah, exactly. So essentially, a CPU is what runs all the stuff, all the instructions in your code, right? So essentially, you take your C code and you basically plug it into a CPU, and the CPU just goes first instruction, second instruction, so on and so on and so on. And essentially, it has this like program counter that just goes through each instruction and says, okay, what am I doing now? Okay, next instruction. What am I doing now? Next instruction. Okay. So let's present again. So why don't we talk about how the CPU will, when we call a function, how it'll handle calling a function, right? Because essentially when you call a function, right, it has to jump somewhere else, right? And then read those instructions, then come back, right? So essentially we have to figure out how that works. So um, let's just say, right, that we are assembling some furniture, right? And essentially, what do we have? Well, and essentially like you have to keep track of what you're thinking before, right? You have to keep track of which step you were on before, right? So you could come back to the step. And then you have to go to the other steps, get those information, and then bring it back, right? So essentially your stack does the exact same thing. So, if we go back to here, so as you can see, this is like the thought that we had originally, so we had to keep track of that. Then we put in the two things that we need to get, right, over here. And then we say, okay, after this, we had to come back to what we were doing. And then over here, you get the results of your function and you poop it out, right? So essentially, the stack is the same thing, right? So over here, it basically puts in the arguments for the function. It puts where it has to go back. RIP stands for return pointer. And then this tells you where to like where your previous stack frame was. So in this case, your previous stack frame was somewhere over here, and then it puts in your local variables and all the stuff you get from running it, right? So if we were running this function, right, like what do we have to do to call foo? What do we have to keep track of in the stack? What do you guys think is the first thing we got to put in the stack for our foo to call foo? Got 3 arguments, so what do you got to do with those arguments? Anything? Where were we? Okay, there. Anybody? No? Okay. Well, essentially, the stack, you first have your int I equals 1, you put that on the stack, okay, that's one of your local variables. Then you put on your arguments, right? Okay. And then you put in your where you should return to, right? Like where in the code you call the function, right? So there's an instruction right here that says call foo, right? So essentially it'll keep track of where it was, so it could come back, and then it'll keep track of where the variables for main are, right? So they're over here, so we had to tell ourselves that. And now we have our new frame set up, right? So essentially now we can just call foo and we're good. So why is this relevant? Okay, so this is less technical, so if you guys didn't understand any of that, has nothing to do with that, but it's basically telling you guys how buffer overflow works. So essentially, let's just say there's this airport terminal, right? And essentially when you type in your name, sorry, I should not give that away. But basically when you type in your name, it could overflow and like cover up the other stuff, right? So, so what could Alice put as her name in order to get her to first class? Any ideas? Basically, when she makes her name really long, right, it'll like cover up this, right? So how could she make her name? How could she make it so that she gets first class instead of coach? Any ideas? Well, basically, she could just add a bunch of spaces after her name, right? It'll be Alice Smith, space, 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 space. And then you put first, and it covers up the coach perfectly, right? So if you do that, then essentially, anybody reading this will actually see that, oh, well, Alice Smith should be first class, even though she isn't, and all she did was just add a bunch of spaces, right? And then you could even like override the special instruction by adding enough spaces, and that's pretty cool. So essentially, buffer overflow is the exact same idea. And what's cool is that if we have our array here, we don't only have to override local variables, we can also override where functions return to, so it's kind of cool. And you can even override the arguments of functions. So why don't we just try some challenges, because this will be fun. Okay. And let's do some binary exploit. And we'll do overflow 0 first, because that is the easiest one. And then we'll go to the shell. By the way, picoCTF 2021 is happening starting tomorrow. It's like a 14-day competition, so if you guys want to sign up for that, make sure to do that. I don't know why it's being so laggy, but this might be too laggy. Okay. So if we go into the problem, we cat vuln.c. Oh, did somebody put something in chat? Yeah, CDFs are pretty hard, but they're pretty fun too. So essentially, what this is saying is that if we manage to make a segmentation fault, which basically means that we like mess up something in the code, then it'll print out our flag, right? So if we're okay, so essentially it's gonna put our input into a buffer with size 128, right? So how long do we have to make our string in order to make it segment fault? Or, well, I mean, it's kind of obvious, right? We just need it to be like somewhat longer than 128. So what we could do is we could do /vuln, right? And we could put in a really, really long string. Let's see, make it really, really, really long. Okay, hopefully that's more than 128. Probably isn't actually. Okay, let's keep going. Hey, we got it. Easy peasy, lemon squeezy. So then you could just take the flag and you can put it in here. Nice. Okay, so now we want to do something a little bit harder. So let's look at this dude. Actually, I'll just go to the folder in here. Hold up. Okay, so if we cd into there, then if we ls cat vuln.c. Okay, so essentially you can see that there is this thing, right? And essentially we have our same setup where we have a buffer. We use getS, which is vulnerable, right? And essentially we want to make it so that we could jump to the flag and make it print the flag, right? So does anybody have an idea how we could do this? Like which variable do we want to override in this thing? Which variable might be useful to override? Yeah, this is kind of hard, but the answer is the return address, right? If we could change where the function returns to, then we can make it return to the flag function and make it print out the flag for us, right? So essentially what we could do is we could look at the code itself, the assembly code, objdump vuln -objdump -d vuln, and then pipe less. Okay. Okay, let's find our main function. Okay, nice. We found our main. Let's find our vuln function. Okay, so that's where our vuln function is, right? And essentially we want to make it return to this memory address. So let's keep track of this memory address. This is where the code is stored, right? Let's put that in another tab. Okay. And essentially we want to change the return address of vuln. Okay, so let's go to vuln. Okay, so basically we have this. Oh, bruh. This is lagging too hard. Okay. So we are here, and essentially, bruh. Hopefully this. Okay, there we go. So essentially, our like buff, like the thing that we're writing into is here, right? So, or sorry, this is it, right? So what is 48 like if we convert it from hex to decimal, right? If we are converting it from this 0x means it's base 16, so how do we convert 48 to base 10? You basically just do 4 times 16 plus 8. Okay, and then essentially 4 times 16 plus 8 is 72. That takes us up till here, and we want to override this, right? So if this is 4 bytes, right, we have to add 4 more, and then we get to start overriding this. So essentially what we could do is we could write a Python script, and we could do vim, let's see, we'll call it overflow over f.ty. How about that? And essentially we want to print a string to help us with this, right? So we want to have our string be 76 A's long. Hold up. A times 76. And then we could add in the address we had, right? So what was the address we had? This, right? And essentially you got to do it a little bit backwards because like in a computer that stores it backwards. So we do slash x e6 slash x what? 85 slash x what's next? 0408. 08. Okay. I don't know why it's being so slow, but once it finishes, we should be good. Okay, let us save that. Bro, this thing is making my computer go crazy. Okay, so then we could basically just put. So if we if we run the thing just like normally, and we put in like a really long thing. So this is how it normally works, right? It's returning to this address. Then if we make it really long, the string really long, then essentially the return address actually changes. So instead of being that, it changed into some random ASDF, right? Literally you can see the like there's a 61 in there, so that's like A, and then 6A is S or D or something, I don't know. But yeah, you can basically see that we overrode it. So essentially if we run our Python script, overflow.py, and we put it into our C program, we should get our flag, hopefully. Oh, whoops. Python overflow f.py type./von. Oh, will it give us? Hey, we got it. Very nice. And now we could submit this and get our points. Very nice. Okay, so basically Pico has a lot of these fun challenges, so if you guys are interested in that, make sure to sign up. And there's a lot of different things. If you're not interested in like hacking C programs, you could also hack websites, or you could like learn your terminal skills, or you could do crypto. I know a lot of you guys are into math, so crypto is pretty cool for that. And then there's forensics and reverse engineering. Okay, so if you guys are interested, here is the flag. But other than that, we are done for today. Oops. There we go. Alright, thank you guys for coming. Other than that, we are done. So see you guys next week.